Dear students, welcome back to the lecture series on solid state. In this session, we will have a detailed discussion on various crystal systems. We will see what are crystallographic point groups, what are the different types of crystal systems, and what are meant by Bravais lattices. Before moving on to today's session, we will discuss the assignment questions of previous class. So, the first question was, what is each point or position of particle in a crystal lattice termed as? Option A, lattice index, option B, lattice point, option C, lattice lines, and option D, lattice spot. So, we have seen that a crystalline lattice is represented by a periodic array of points in a particular geometrical pattern, and when these lattice points are replaced by the motifs or the constituent particles such as atoms, ions or molecules, then that is called a lattice point. Okay. So, the lattice point describes the position of a particle in a crystal lattice. So, the correct option is option B, lattice point. Second question, which of the following is regarded as the repeatable entity of a 3D crystal structure? Option A, unit cell, option B, lattice, option C, crystal, and option D, Bravais index. So, the repeatable entity of a 3D crystal structure means when that entity is repeated, you will get the entire 3-dimensional crystal structure, and that entity is nothing but the unit cell. And we have seen that a unit cell is the basic building block. So, a basic building block of the crystal, which when repeated will give you the entire 3-dimensional crystal structure. So, the correct option is option A, that is unit cell. The third question, how many parameters are used to characterize a unit cell? Option A, 6, option B, 3, option C, 2, and option D, 9. We have seen that a unit cell is characterized by the intercepts made on the 3 crystallographic axes, namely A, B, and C. There are also the axial angles denoted as alpha, beta, and gamma. So, a unit cell is characterized by these 3 intercepts A, B, and C, and also the 3 angles alpha, beta, and gamma, and these are called the lattice parameters. So, total you have 6 parameters including the 3 intercepts and 3 angles. So, the correct option is option A, 6 parameters are used to characterize a unit cell. Question number 4, if a crystal plane makes intercepts 1 by 2a, 1 by 2b and c, what are the Miller indices of the plane? So, we have the intercepts given 1 by 2a, 1 by 2b and c. So, in the last class we have seen the steps for finding out the Miller indices. So, first we have to determine the Weiss coefficients of or Weiss indices. So, the coefficient of A is 1 by 2, the coefficient of B is again 1 by 2, and the coefficient of C is unity. So, that is 1. Now, what is the second step? You have to take the reciprocals. So, when we take the reciprocals, so that will be 2, 2 and 1. So, there is no need to clear the fractions because the denominator is 1. So, the Miller indices will be 2, 2, 1. So, the plane is a 2, 2, 1 plane. The last question, a face makes intercepts 2a and 3b on the x axis and y axis respectively and does not cut the z axis at all. So, what are the Weiss indices and Miller indices of the face? So, on the x axis the intercept is 2a, on the y axis the intercept is 3b and it does not cut the z axis. So, that is parallel to the z axis. So, it will be infinity c. So, what will be the Weiss indices? Weiss indices are nothing but the coefficients of the intercepts. So, we have the coefficient of A 2, coefficient of B 3 and the coefficient of C is infinity. Okay. Now, we have to find out the Miller indices. So, you have to take the reciprocals. So, we have 1 by 2, 1 by 3 and 1 by infinity. And in order to get the Miller indices, we have to clear the fractions. So, multiply with a smallest common number. On the denominator we have 2 and 3, so 6 will be a suitable choice. So, if we multiply each fraction with 6, 1 by 3 into 6 and here it is 1 by infinity is actually 0. So, there is no point in multiplying it with 6. Okay. So, here you will get 3, 2 and 0. So, the Miller indices will be 3, 2 and 0. Now, we will move on to today's session. In the previous classes, we have seen the symmetry elements present in a crystal. And what is a symmetry element? It is any geometrical entity such as a line, a plane or a point with respect to which a symmetry operation may be performed. Now, what is a symmetry operation? It can be either rotation, it can be reflection, it can be translation, whatever it is. So, a geometrical entity such as a line, a plane or a point with respect to which a symmetry operation may be performed is called a symmetry element. And these are the elements of symmetry present in a crystal. We have an axis of symmetry or proper rotation axis. We have a plane of symmetry or a mirror plane and also we have a center of symmetry. Now, if we take a particular crystal, there may be a combination of symmetry elements or there will be a combination of symmetry operators that can operate on a lattice. So, as I said earlier, the symmetry operators may be rotation, translation, reflection, etc. Okay. So, group of symmetry operators or a combination of symmetry operators means there can be a combination of symmetry elements present in a crystal structure. So, this combination or a group of symmetry elements is known as point group. Now, a interesting aspect of such a point group is that there will be all these symmetry elements will intersect at a common point in a crystal, and these symmetry operations will make this point unmoved in a crystal structure. Okay. So, if we consider the crystal as a whole, there will be a combination of symmetry operators or a combination of symmetry elements, and when we do any symmetry operation, there will be a common point in the crystal such that all these symmetry operations will make this point unmoved or unchanged in the crystal lattice. Okay. So, such a combination or a group of symmetry elements is known as point group. A point group operating on a crystalline solid must be such that every symmetry element of the group can operate on a lattice, and such a point group is more specifically termed as crystallographic point group. As you can see in the heading here, it is a crystallographic point group. So, if we consider a crystal lattice, there will be a group of symmetry operators and a point group operating on a crystalline solid such that every symmetry element of the group can operate on that particular lattice, and such a point group is termed as a crystallographic point group, or it may be also defined as a group of symmetry elements that can operate on infinite three-dimensional lattice so as to leave one point unmoved. As I mentioned earlier, there will be a point in a crystal in which when a symmetry operation is carried out, when any of the symmetry operations is carried out, that will retain that point unmoved or unchanged. Okay. So, that is called a crystallographic point group. And in the previous slide, we saw that there will be a group of symmetry elements. However, symmetry operators can combine in surprisingly smaller number of ways, and it was observed that only 32 combinations are possible, and these 32 combinations of symmetry elements represent the only combination of symmetry elements that crystals can have. So, when crystals having the same point group symmetry are said to belong to the same crystal class. Okay. So, there may be possible a group of symmetry elements present in a crystal lattice. However, their number, that is such groups of symmetry elements or the combinations are restricted to 32. So, in other words, we can say that there are the 32 crystallographic point groups constitute the 32 crystal classes. These 32 crystal classes possible based on considerations of symmetry and the internal structure fall into 7 basic systems, and these 7 basic systems are termed as the 7 crystal systems. There are 32 possible combinations of symmetry elements. So, these 32 crystal classes based on symmetry and the internal structure can be further classified into 7 basic systems. Okay. So, these 7 basic systems are known as the 7 crystal systems. And these 7 crystal systems are distinguished on the basis of their lattice parameters. And what are the lattice parameters? We have 6 lattice parameters, that is, we have the intercepts made on the 3 crystallographic axes denoted by A, B and C, and we also have the axial angles, this alpha, beta and gamma. So, these are the lattice parameters. So, based on the intercepts and the axial angles, there are 7 basic crystal systems, and each crystal system is thus specified by the shape and symmetry of the unit cell. Now, let us see what are the 7 crystal systems. We have a cubic crystal system, tetragonal, orthorhombic, monoclinic, triclinic, rhombohedral and hexagonal. Now, let us see each crystal system one by one. The first one is a cubic crystal system. On the screen, you can see a cubic crystal system. Here, all the 3 crystallographic axes are of equal length and intersect each other at right angles. Or we can say A equals B equals C. All the sides are equal since it is a cubic form, and all the angles, that is alpha equals beta equals gamma equals 90 degree. These cubic unit cells have the most symmetry possible, or the highly symmetric system is a cubic crystal system with all sides equal and all angles equal. The next one is the tetragonal crystal system. In the tetragonal system, as you can see in this figure, 2 crystallographic axes are of equal length, while the third axis is different, and also it is perpendicular to the other 2. Okay. So, we can represent the parameters as A equals B not equal to C. 2 sides are equal, but it is not equal to the third side. Then the axial angles, they are right angles, that is alpha equals beta equals gamma equals 90 degree. Okay. So, this creates a rectangular prism shape for a tetragonal crystal system. Next is orthorhombic crystal system. In an orthorhombic system, we have the 3 axes of different lengths and all of which intersect at right angles. So, we have A not equal to B not equal to C, and alpha equals beta equals gamma equals 90 degree. So, in orthorhombic system, with all the 3 sides unequal and the axial angles at 90 degree, the resulting shape is a rectangular prism, but the sides are not equal in length. So, next is a monoclinic crystal system. In a monoclinic system, we have 3 axes of different lengths, okay, that is A not equal to B not equal to C, alpha equals gamma equals 90 degree, but beta is not equal to 90 degree. So, this creates a prism shape with one angle that is not a right angle. Okay. So, we have alpha and gamma equal to 90 degree, but beta is not equal to 90 degree. Now, next one is a hexagonal crystal system. Have 2 axes of equal lengths and intersect at angles of 120 degrees. So, we have A equal to B not equal to C. We have alpha equals beta equals 90 degree, but an interesting feature you can see in a hexagonal shape, one of the angle, that is gamma, equal to 120 degree. So, this will result in a prism shape with a hexagonal base. So, next is a rhombohedral crystal system or a trigonal crystal system. Rhombohedral crystals have 3 axes of equal length, all of which intersect at oblique angles. Oblique angles means not equal to 90 degree. So, we have A equals B equals C and alpha equals beta equals gamma not equal to 90 degree. And the resulting shape is a rhombohedron, which is like a cube, but if that cube is distorted into a shape, we know that a cube has exactly right angles, all 3 axes are at right angles. But suppose that cube is slightly distorted, then the angles will not be equal to 90 degree. So, such a shape is called a rhombohedral or a trigonal. Okay. The next is the triclinic crystal system. And in this system, the 3 crystallographic axes are of different lengths and they intersect at oblique angles. So, that means A not equal to B not equal to C, and also alpha not equal to beta not equal to gamma not equal to 90 degree. Okay. So, all the sides are not equal, all the angles are also not equal. Okay. So, in more convenient way, we can also represent it as A not equal to B not equal to C not equal to A. So, this actually demonstrates the complete inequality of the 3 sides. So, this results in a crystal shape that lacks any form of symmetry, or we may say that the triclinic system is highly unsymmetrical. Okay, so highly unsymmetrical system is a triclinic system. So, these are the 7 crystal systems. On the table, you can see the 7 crystal systems with their lattice parameters. And for the cubic system, the essential symmetry element is a 4 3-fold axis. And typical examples are given here. We have the crystals of sodium chloride, potassium chloride, calcium fluoride, diamond, alums, etc. all belong to the cubic crystal system. So, next is the tetragonal, and the essential symmetry element is 1 4-fold axis. The examples given, we have SnO2, then titanium dioxide TiO2, then lead, tungstate, all these are examples for a tetragonal system. Now, next is orthorhombic system. The essential symmetry element, we can see there are 3 mutually perpendicular 2-fold axis, C2 axis. The examples, we can see the rhombic sulfur is a very good example for an orthorhombic system. We have barium sulfate, potassium sulfate, lead carbonate, all belong to the orthorhombic system. So, next is the monoclinic system. The essential symmetry element is 1 2-fold axis or a mirror plane. Monoclinic sulfur belong to the monoclinic system. We have calcium sulfate, sodium borate, all belong to the monoclinic system. The next is the hexagonal, characterized by the essential symmetry element, that is 1 6-fold axis. A typical example is graphite. Graphite has a hexagonal structure. Zinc oxide, mercuric sulfide, cadmium sulfide, all these belong to hexagonal crystal system. So, next is a trigonal or rhombohedral with the essential symmetry element, that is 1 3-fold axis. So, sodium nitrate NaNO3, then we have antimony, bismuth, all belong to the trigonal system. Then the last one is the triclinic system, which is highly unsymmetrical. So, no axis or planes of its particular symmetry. So, potassium dichromate, copper sulfate, then boric acid all belong to the triclinic system. So, till now we have seen the 7 types of crystal systems distinguished from one another on the basis of the lattice parameters, that is the axial intercepts and the axial angles. We have seen that a crystalline solid is characterized by a regular repeating arrangement of its structural units, and these structural units we generally call it as motifs or bases. So, on the screen you can see a crystalline 3-dimensional crystalline structure of the sodium chloride crystal. So, you can see that there is a regular repeating arrangement of these structural units or motifs. And we have also seen that these motifs are placed on certain imaginary points that constitutes a lattice. So, when these imaginary points are replaced by these motifs, then these are called the lattice points. Now, the peculiarity of each lattice point is that the surroundings or the environment around each lattice point will be identical. Auguste Breve, a French physicist, demonstrated in 1848 that there are only 14 unique 3-dimensional lattices that can fill space without gaps. So, these lattices represent the various ways atoms can be arranged within a crystal structure, and the symmetry of these lattices corresponds to the 7 crystal systems. We have seen that there are 32 possible combinations of the symmetry elements, and that falls into 7 crystal systems which are distinguished from one another based on their lattice parameters. Okay. However, on the lattice we can arrange the lattice points in any repeatable pattern, but that is restricted to 14 unique 3-dimensional lattices that can fill space without gaps. So, among the 7 crystal systems, 14 basic unit cells exist which may be packed together to completely fill a space. So, these 14 unique cells or unique 3-dimensional lattices are referred to as the Breve lattices. Okay. So, these 14 basic unit cells will be packed together to completely fill the space. Okay. So, now let us see different types of unit cells. We have a primitive or a simple lattice represented as P. So, this is in a cubic unit cell. Okay, so, let us draw a cubic crystal. So, here we are considering the cubic type. Okay. So, in a primitive or a simple lattice, the motifs or the structural units will be placed only at the corners. So, if we take a cube, you can see that there are 8 corners. Okay. So, the motifs are placed only at the corners. So, each crystal system has a primitive unit cell. Okay. Here we are considering only the cubic one for the representation. However, each crystal system will have a primitive unit cell. So, motifs are placed only at the corners. The second type of unit cell is a body centered or inner centered lattice represented as I. Okay. So, as the name suggests, in a body centered lattice, the motifs will be placed at the corners and also at the center of the body. Okay. Let us see. Okay. So, the motifs at the corners, we have 8 corners here. Plus there is a motif at the center of the body. So, such a type of unit cell is called a body centered or an inner centered lattice. So, next is a face centered lattice or face centered unit cell. So, in this type, the motifs are placed at the corners and also at the center of each face. Okay. First, let us draw the motifs at the corners. Now, in addition to the motifs at the corners, the motifs or the atoms will be present also at the centers of each face. So, on the top face 1 and on the bottom, third one here, the fourth one at the center of this face, the fifth one on the center of the front face, and also there is a face on the back. So, the sixth one here. Okay. So, in addition to the motifs at the corners, there will also be atoms or motifs present on the centers of each face, and such a unit cell is called a face centered lattice or face centered unit cell. And the next is a base centered or end centered lattice. So, in this, the motifs are placed at the corners and also at the centers of 2 opposing faces. Okay. So, let us consider a the motifs are present at the corners and also at the centers of 2 opposing faces. Okay. So, let us consider the face on the top and the bottom. So, one motif or atom will be here and the other one will be here. Okay. So, on the 2 opposing faces. So, such a type of unit cell is called a base centered or end centered unit cell or end centered lattice, and generally represented as C, or it can also be A or B. Okay. So, these are the 4 general types of unit cells. Now, coming to the 14 breve lattices. If we take a simple cubic system, we have the atoms placed at the corners, that is a primitive type. We have a face centered type and also we have a body centered type. Now, if we consider the tetragonal system, we have the primitive type and also body centered. When we consider the orthorhombic system, you can see that it corresponds to a primitive one, a body centered, a base centered and also a face centered. all the 4 types of unit cells are present in orthorhombic system. And in rhombohedral, it's a primitive type. Hexagonal is of primitive type. Then monoclinic, again a primitive type, and also a base centered, and triclinic having a primitive type. Okay. So, all these together corresponds to the 14 Bravais lattices. So, till now we have seen the 14 Bravais lattices, that is how the constituent particles or the atoms are arranged throughout the 3-dimensional lattice, that is in 14 different ways. Okay. And there are general 4 types of unit cells. So, in this session we have seen the 32 crystallographic point groups or crystal classes, the 7 crystal systems distinguished on the basis of their lattice parameters. The crystal systems range from the highly symmetrical cubic system to the highly unsymmetrical triclinic system. Depending on the arrangement of atoms in the lattice, there are 14 Bravais lattices. The types of unit cells includes a primitive cell in which the atoms are present only at the corners, a body centered, face centered, and a base centered or end centered unit cells. Now, let us see some questions based on today's topic. The first question, most Bravais lattices are of the type option A, primitive unit cell, B, body centered unit cell, C, end centered unit cell, and D, face centered unit cell. The second question, most unsymmetrical crystal system in terms of axial distances and angles, monoclinic, triclinic, rhombohedral, and hexagonal. Question number 3, a unit cell that contains lattice points only at the corners is known as option A, primitive unit cell, B, end centered unit cell, C, face centered unit cell, and D, body centered unit cell. Question 4, the axial relationship of a monoclinic crystal system is given as, you have 4 options here. Question 5, the axial angles of a hexagonal crystal system are given by, 4 options. You have to find out the axial angles of a hexagonal crystal system. Okay. So, please try to find out the answers. We will discuss it in the next class. Thank you.